We are doing chapter 10.2, The Sun and the Stars. So it was two separate chapters, the sun, and the next chapter was the stars. But since they're like sort of the same thing, I mushed them into one chapter. So it means more work for you guys, but let me put on, I gotta put on the chat so I can see you guys ask questions. Yeah. Go. Hello, Kevin. All right. Boom. Oh yeah, this week vocab is totally optional. You don't have to do it. It's in Quizlet just like beforehand. Okay. Your essential questions or tasks. By the end of this week, you should be able to identify the physical properties of the stars. So like, what are the different properties of the stars? You'll learn is temperature, size, color, age, stuff like that. Honestly, I don't know what that one means. I think it's sort of the same thing. Explain solar, those are also the same thing. They're all sort of the same thing. And we also know that one. And compare actually that one you don't have to do. Where did I get these from? All right, so basically just the first one. That's all you gotta do. Because this electromagnetic spectrum is next week. And when it says electromagnetic spectrum, it just means all the colors pretty much. And like X-rays and stuff like that. We'll get to it next week. All right. All right, we can start off with the video. I don't know what it is though. I made this at 1 in the morning last night, so I do not know what anything is. I think I just wanted to show you guys what the sun looks like. That's it. It's pretty. Now, this is seen through a special filter, so it's not like the exact perfect color, but that's what the sun actually sort of looks like. The sun is a ball of gas. Remember, many people think that the sun is like a solid, like you can like land on its surface. It's a big ball of gas. Technically, if you had this magic power, you could zoom, just like Jupiter. All right, and we're going to talk about what those loops are, everything that comes off of it. We'll talk about what the dark spots are. Elena, you got lots of question. I'm going too fast. I'm just telling you all the stuff we're going to go over. This is just a preview. You have a question, Miley. Go ahead. Miley is awesome. I would say what different characteristics make up stars? That's all you need to know. How do we define different characteristics of stars? All right. Yeah. All right. On to the next one. I just wanted to show you what the sun looks like. There's lots more videos, including this one. Here's your first video. Actual video.
While billions of stars are scattered throughout the universe, the one at the center of our solar system plays a special role for us here on Earth. Our sun formed about 4.5 billion years ago in the Milky Way galaxy's Orion spur. It was born when a cloud of dust and gas, known as a solar nebula, collapsed. And in the middle of this formation, matter condensed into a burning ball of gas that became our sun. The sun's fiery nature on a tremendous gravitational pull and an extensive magnetic field helped it to become the heart of our solar system. The sun can be divided into 6 layers or regions: the corona, the chromosphere,
the corona,
the photosphere, the convective and radiative zones, and the core.
It has a
in
core.
terms of atom count, the sun is about 91% hydrogen from the sun's fuel, 8.9% helium, and 0.1% heavier elements such as carbon and nitrogen. Due to the sun's extreme temperatures, these elements stay in a gas-like phase called plasma. In the core, temperatures reaching at least 27 million degrees Fahrenheit, combined with the sun's powerful gravity, fuse together hydrogen molecules to create helium. Called thermonuclear fusion, this releases an enormous amount of energy in the form of radiation, electricity, solar wind, and, as we experience on Earth, life-giving heat and light. Such volatility is contained thanks to the sun's tremendous gravity. It's strong enough to hold the solar system intact and is primarily due to the sun's size and mass. Our sun is the largest and most massive object in the solar system. It's more than 100 Earths wide and could theoretically fit all 80 planets inside nearly 600 times. It also contains approximately 99.8% of all the mass in the solar system.
Which we should already know.
Because of this mass, the sun has a great pull on the fabric of space, creating a gravitational force that causes nearby planetary bodies to be drawn toward it. This gravitational pull allows the sun to hold together a system of 8 planets, potentially dozens of dwarf planets, at least 170 moons, and countless comets and asteroids. Without the sun's gravity, these celestial bodies would drift off into deep space.
Whee!
Another critical property of the sun is its magnetic field, which encapsulates the entire solar system. Called the heliosphere, this force field protects the planets from harmful cosmic radiation. It's caused by the sun's plasma pushing electrically charged particles toward the star's poles. This process turns the sun into a giant magnet. Although the sun's magnetic field is invisible to the naked eye, its effects are noticeable. On the sun's surface are dark areas called sunspots, which mark strong pockets of magnetism. On Earth and on some of the other planets, the sun's magnetic field interacts with their atmospheres, resulting in beautiful auroras. Despite its size and strength, the sun will not last forever. In about 6.5 billion years, it will run out of its hydrogen fuel, expand to envelop Mercury, Venus, and even Earth, and then collapse into a small star known as a white dwarf. In the meantime, the sun will continue to play a critical role in the system that bears its name. The sun's protected magnetic field, tremendous gravitational pull, and ability to create vast amounts of energy will protect, contain, and give life to our solar system.
So a couple cool things from that is that we don't realize that, one, Earth's magnetic field protects us a lot from the radiation from the sun. Like without our magnetic field on Earth, we'd all die. First of all. And then on top of that, the sun has a magnetic field that protects us from all the radiation outside our solar system. Like a ton is trying to get in our solar system, but the sun protects us. Without the sun, so to speak, we'd all die. Or turn into Hulk. I don't know which one. Let's see, anything else I want to talk about from that video? There's a lot of stuff in there. You guys should already know that it's 99% of all the mass in the solar system. You should already know that it's mostly made up of hydrogen and some helium. They talked about the nuclear fusion is when hydrogen molecules come together and create helium. We'll talk about that a little bit later because it's sort of important to the death of a star. The sun is a spicy meatball. Thank you, Cole. I feel bad for the 6.5. Yeah, because our sun is also halfway through its life, and we'll talk about the life of a star today. And so another 6 billion years, it's going to go, what'll actually, I don't know, I didn't watch the video, I was sort of looking at the video, but what'll actually happen is that towards the end of a star's life, it sort of gets bigger and turns into a red giant. And as it gets bigger, it's actually going to consume Mercury, Venus, and Earth. Just before it dies off. All right, so first slide of actual content, the structure of the sun. Some basic stuff to remember is that obviously the sun is a gas. It's all this helium, hydrogen. It only has a little bit of like the heavier stuff, like carbon and stuff like that. Let's see, it has no solid surface. So technically you could just go straight through it in a way. At 3/4, it's over 3/4 is hydrogen. So basically you do have to know that the main parts of usually any star is hydrogen and helium. Those are like the two big things. What are you guy talking about? Austin shop, so what the heck? Other than that, you don't need to know that it's plasma. I'm not going to test you on that. You do need to know it's a lot of hydrogen and helium, and that's what actually makes the nuclear fusion. I'm not going to test you too much on the structure of the sun. I'm more interested in you guys knowing about what makes a star and the different types of stars and stuff, not just our sun. I won't test you too much on the layers of the sun, which we're going to go over in a second. Just like our Earth, there's a inside of Earth. Remember, our inside of Earth, there's the crust, the mantle, the core. The sun has something similar to that, and it has an atmosphere, just like we have an atmosphere. Remember the troposphere? Now I'm forgetting all the layers, but we have 5 layers. The sun has layers in the atmosphere as well. What about the last question on the quiz? Wait, what? Okay, there's a lot of stuff here. Wait, so the sun won't swallow Mars. They don't think it's going to get that big, I don't think, to swallow up Mars. Actually, it might. I don't know. Did the video say it? Because I think there's a video somewhere in here that shows it. I think it's going to be a little later. All right. My mom wanted to ask because it was Jupiter plus the sun. Oh, the answer was just the sun. The largest, the largest body in our system is the sun. Yeah. If I asked the largest planet, it would have been Jupiter. But the largest body in our solar system is the sun. All right, next one. And I love the pictures of the actual sun. All right, so I'm not going to test you on which one's which or the layer. I do want you to sort of know the names, but I'm not going to, obviously the core is in the center, but I'm not going to make you memorize the different layers. You just have to know there's an interior, a core to the sun. The core is extremely hot, 27 million degrees Fahrenheit. Sort of high. You know, our stove is 400. If you touch a hot stove, burn yourself, 400 degrees, 27 million. I wonder how fast you would disintegrate. So there's the core, and then after the core, there's a radiative zone, and that radiative zone is responsible for like all the light we see and creating like photons that come towards Earth. It sort of starts at the core, goes through that zone, and then shoots out. It takes like, there's a video, it takes like, I think it's like 100 million years for a ray of light to get from the core to Earth. It's sort of weird, but that was in my research. And then it has its own convection zone. We all remember convection. Hot stuff rises, cold stuff sinks. It's sort of weird to think that there's cold stuff on the sun, but it's just colder. You said how long does it take? Oh, well, you don't have to know that. You don't have to know that. If it's in the video, we can talk about it, but I don't want to say something wrong. I just know that like in this zone, that's where like the light and the electromagnetic radiation comes from. And it takes a while to make its way from here and then out and towards Earth. Yep, just do your best you can. If you mess up or I go too fast, you can always watch this later. But I don't want to pound this too much because I don't think you're ever going to be tested like on the FSA. What is the middle layer of the sun called? Oh, the radiative zone. I don't think you're going to need to know that. You might need to know it has layers and stuff like that, but I don't think they're going to ask you that. They're going to ask you some different stuff on the stars. Miley, Mr. G, cans you stops. Stop. What? Can you leave? Yeah, Miley, you can leave. You never have to be here. All right, I'm going to keep going. It's not too important. Okay, now this is also not too important, but it's a little bit more important to understand. Now the sun has an atmosphere, like the outside. All right, the furthest, like our exosphere, is the sun's corona, and it extends very far out, and it is very hot. Which one are we talking about first? Okay. There's a corona, a chromosphere, and a photosphere. I'm going to go over each one right now. All right. And remember, it's primarily made out of hydrogen and helium, the same stuff. So. All right. So the photosphere is the part that we can see. All right. So when we look at the sun, we're actually looking at the photosphere, which is not on the outside. It's sort of deeper down inside. We don't actually look, when we look at the sun, we don't see the outside part. Just like we can't see the atmosphere, like we can't actually see something like the chromosphere, but we can see this photosphere. And that's all I guess you need to know is that the photosphere is the one you can see when you look at the sun because it's dense enough to be visible. What do stars and onions have? Oh my God. Really, Cole? The other layer is the chromosphere, and you can only see it during a solar eclipse. Otherwise, you don't see it. During a solar eclipse, you'll see it on the outside of the moon that's going over it. But that's it. You're not going to be able to see it. It's the reddish glow part on the outside. Yeah, chromosphere. It's on the outside. What do we write? Just write chromosphere can't see unless solar eclipse. Honestly, I'm trying to think of what I'm going to put on the quiz, and I don't think I'm going to put a lot of this stuff. If I do, it's going to be very easy. You might just have to know the different names. Like I might say, which one of these is not a layer of the sun? And I'll say photosphere, chromosphere, mantle. And you'll have to say, oh, mantle is part of the earth. So that's not part of the sun or something like that. Oh, the photosphere, I'll go back. The photosphere is the part that you can see. The photosphere is the deepest visible surface of the sun. You can directly look at it. Do not directly look at it. You will get damage to your eyes. What about the selfie sphere? What? All right. Looking at the chat. All right. And then the last one is the corona. That's like on the very outside, the very, very outside. You can't really see this. Like when you look at the sun, it's sort of like a white outline sort of thing. This is the part that's like sort of dangerous to us. It sends out like the solar wind that we sort of talked about last time. Lots of polarized, electrically charged particles. If we didn't have a magnetic field, it would kill us all from radiation. I think it's too much, honestly, too much for me to make you guys memorize the 3 layers on the inside and the 3 layers on the outside and like all the different parts of it. Like that's just too much. So that's not fair. What, Elena? See you mouthing to the chat, sis. Go back, go back, go back, go back. Okay, go back. I'm going back. I'm going back. Did I go back? Yeah, I went back. Let's see. While she's doing that, what else can I talk about this? Nah, I'll just give you some time. Let's see. Oh, we're just gonna wait. All right. Sorry, Lana, we're going. Did Elena leave? Oh no, she just turned off her thing. Okay. All right. Features of the sun. So now this is more important. I will probably test you on these. These are things that we can see about the sun. The first thing that we can see on the sun are called sunspots. This picture up here. They are dark spots on the sun. These dark spots are not burnt spots. They are areas of the sun that are cooler than around it. And apparently the colder parts result in a darker, it doesn't emit as much light. So the dark spots are the colder spots on the sun's surface. But they're still very hot. It's not like, oh, we can land there. Oh, hello, Dylan. Welcome. Oh, did I ever tell you that I went to eat at your dad's restaurant? I did. I should have got the fish, though. I didn't like your suggestion, the pork. The fries were amazing, though. All right, sorry. This is recorded. I shouldn't talk about that. All right, so sunspots are the dark spots. They're colder. Okay, so then there's something called prominences. And then these right here, they're giant loops of magnetic polarized gas that usually links from hot spot or from sunspot to sunspot. So like when there's like two sunspots close to each other, a lot of times this loop will occur that sort of bursts out. That goes out and comes back in. I don't know why it happens. Maybe I just didn't do enough research, but I don't know. Go back to the corona. The corona is just the outside layer, but that's very hot and where the solar wind comes from. All right, so these are prominences, all right? And then sort of like a super prominence, like when prominences sort of come together, when these loops connect with each other, when there's more than one, a lot of times they sort of explode or erupt, and that's what a solar flare is. And solar flares are the things that sort of shoot at Earth and can become very dangerous. They're ginormous. There's like a little Earth to show you how big solar flares can be. If a solar flare is strong enough, it can literally wipe out all technology. It'll literally just destroy everything that's like a piece of technology. Pretty cool. So if we want to go back to the Stone Age, we just need sun to sort of produce a strong enough solar flare. Where the restaurant? Oh, his restaurant? It's in Bonita on Old 41. He can type it. He's the advertising man. Why does Krishna say hello to me? Oh, I don't know, Kevin. Let's see. Anything else? It's like the Dark Phoenix. Yeah, sort of. Pretty much. All right. Oh, is Lena still here? I can't even see. Yeah. Hopefully you got everything, Lena, because I'm about to go on. Sunspots, dark areas, prominences, giant, huge loops. This stuff is also in the vocab. So if you need to practice like what with these, just do the vocab. The vocab is extra credit this week. Oh yeah, here you go. Here's a video of one. I think. There you go. This is real, by the way. This is not like a simulation. They're very big. Now, since it's like a perfect loop like this wouldn't be like a solar flare. Solar flare looks more like an explosion and sort of shoots out. This is a prominence. Prominence is just like a nice, clean loop. It's pretty. Pretty hot. Oops. All right. I don't think anything changes. Yeah. Eventually it comes back down. All right. That's it. Austin, mute, please. Oh, I can mute Austin. All right. Bye, Austin. What is this? Why did I put this in here? Oh, okay. Okay. Wait. So this is where we start getting into the scary stuff, I guess. But I didn't go too scary. Like I told you, I did not put that noise. Who has their... Must be cold. All right. It's going to talk about our sun, the life of a sun, stuff like that. And then we're going to start getting into different aspects of our sun even more. All right. Here we go. Can I go full screen? Oh. Yeah.
It's one of my favorite topics. Stars change throughout their lives, just like we do, only they live for billions of years instead of decades. They start out as clouds of gas and dust called stellar bursts. The force of gravity slowly pulls particles inside these clouds closer together, causing dense clumps to form. If a clump grows large enough, the pressure caused by gravity inside one of these baby protostars begins to generate.
So we're gonna go over in a second, but a baby star is called a protostar.
And pressure builds until nuclear fusion reactions begin to take place in the core. Gravity pulls hot.
You can't hear that much? I don't know why I can't increase my volume. There must be a way. Settings? No. Where's... Maybe if I do... I have you on this. I don't understand. Let me see. If not, you're just gonna have to read the subtitles.
I can manage to get them smashing into heavier helium atoms. Nuclear fusion generates an enormous amount of energy, causing the star to eject. This is the beginning of the longest part of the star's lifetime, or its main sequence.
All right, so I'll stop there too. And we'll talk about this. A main sequence star is like if we're talking about us, it's like from when you're 18 years old to like 50. It's like you're an adult, you're good, you're healthy, nothing's wrong with you, you're living fine, sort of type thing. All right, that's a main sequence star. We have a main sequence star.
Less than halfway through 10 billion year long main sequence. Well, what happens to a star after its main sequence depends on its mass. Astronomers actually don't know what happens to low mass stars, those with less than about half the mass of our sun. They may actually have a main sequence that lasts more than a trillion years, that's longer than the current age of the universe. Mid-sized stars, like our sun, become white dwarfs. Those are super dense objects, about as massive as the sun.
And we're going to go over this all.
Around the size of the Earth, actually. A couple of things will happen before the sun turns into a white dwarf. The sun will begin to die when it uses up all the hydrogen in its core. At that point, the sun will expand, ballooning to many times its current size.
Destroying everything in its path.
Stars in this stage of their life are called red giants because their surfaces cool down to a red glow. Plus, they're really, really big. The sun will start burning helium at that stage, using it to even heavier elements. Eventually, it gets so big that it engulfs the Earth. Oh, don't worry, we'll all be long gone before that happens. It's billions of years away. Anyway, after more than about a billion years as a red giant, the sun will begin to collapse under the pressure of gravity. It will actually get kind of unstable, expanding and contracting and shedding its outer layers in the process. The remains of those outer layers form a big cloud of gas and dust called a planetary nebula. No, they don't have anything to do with planets, they're just called them. But you know, you've probably seen some awesome pictures of planetary nebulas from the Hubble Space Telescope. These are pictures of stars that are in the end stages of their lives. It's kind of like watching what will happen to our sun way before it actually does. Anyway, at the center of a planetary nebula is full of carbon, which, after cooling, finally becomes a white dwarf. Well, that's the route our sun will take, but it's not the only way a star can die.
Yeah.
The star is much bigger than our sun. Collapse so quickly that they explode into a supernova, scattering stellar material far and wide. A supernova explosion can last for a month or longer, and during that time it can be as bright as a galaxy with a billion stars. Clouds of gas and dust that supernovas spew out are what heavy elements are making, and the formation of new stars. sun, with protons and electrons in the form portions of neutrons. What you get is a neutron star. Some neutron stars spin rapid, emitting pulses of radio waves. These are those pulsars. If, on the other hand, the original star was more than 10 times as massive as the sun, its supernova form collapses on itself. It will keep collapsing until it forms a tiny area in a dense called a singularity. We call this a black hole. It's so powerful that nothing within range can escape it. But not even light. And nothing you throw into a black hole will ever come back. We actually have a whole other movie on this. You should go check it out. Well, time to take the trash out. You know, we could just take the trash out to the corner.
All right, so there is a ton there, a lot. And I'm gonna try to go over it all. And I'm gonna try to, wait, what are you doing? Get out of here. Oh wait, I have to take it off full screen. Get out. Stop. Bad, okay. Wait, what the, okay, what's going on here? All right, I'm gonna fix this. Why is this showing up here? Stop it. All right. All right, so I'm not sure if I want to read off of this or if I just want to tell you how a star forms all the way through to how it dies. I might just do it that way and then go through this. So in the beginning, I already told you guys about this. There is a sort of a nebula of gas that's usually made out of hydrogen and helium. Gravity pulls it together. The hydrogen atoms sort of fuse together with so much gravity and pressure, and they go through thermonuclear fusion, make helium atoms, and that's what makes the sun. So once it does that, it becomes a protostar, which I think we'll talk about in a second. Yeah, they're down at the bottom here. That's the first stage. So when, our star first formed, it was a protostar. Then eventually once its, its fusion starts get going, it turns into a main sequence star for most of its life. Now towards the end, there's two routes. I'm actually gonna go to I'm gonna skip a couple slides real quick. I'll go back to this. Come on, come on, come on, come on, come on, come on, come on. Nope, not yet. Not yet. We'll go back. All right, so there's two routes it can go. All right, one, an average star. So a star that's like average sized, like our star, will eventually just become, towards its end, after it uses up all of its hydrogen, its fuel, it's sort of like, oh no, what am I gonna do now? And it turns into a red giant star towards the end when it's running out of fuel, all right? Once it starts running out of hydrogen to create the nuclear fusion, it starts using the helium that it made. And once the helium gets fused together, it creates carbon. And then once it's carbon, there's no more fuel out of it. It can't use it for fuel anymore. It's very heavy. Like it said, it sort of like expands and contracts and sort of sheds its outside parts of the stars. And then that planetary nebula comes in, where it's just gas again. And then at the center of it, we'll just have a white dwarf. And a white dwarf is much cooler than a regular star. There's no nuclear fusion going on anymore. And I'll talk about it in a second. It's just sort of like this glow from like the energy beforehand. And eventually the glow will run out in a couple more billion years. And then you're just left with a black rock, a black dwarf. Now the other route it can go is if it's a huge star. Like after its main sequence, like if it's a ginormous star, not like ours, it turns into a red supergiant. And a red supergiant is ginormous. And we saw some in the video last week of like ginormous stars. Those, when they run out of fuel, they sort of collapse in on themselves really quickly and then blow up. And that's what they said was a supernova. And then depending on the supernova, either you can make a neutron star, which is a very dense star and it spins really fast. And they said something about pulsars, but you're not gonna have to know that. Or it can make a black hole. Black holes are very small, usually, Well, they're not very small, but they're smaller than suns mostly, but they're extremely dense. So dense that everything gets sucked into them because they have so much gravity. All right, let's go back. I just wanted to show you guys the two options sort of that suns have for their life. That's pretty much the only things that can happen to stars. All right, I'm gonna go back now. I'll go through the notes and see if there's anything. All right. You guys already know that it comes from gravity. I said that already. They start out as nebulous. Here's a video of a sort of a simulation of how it forms from a nebula. It sort of just uses gravity and sucks it all in. Pretty much what the beginning of a star looks like, in a way. Anything else that's important in here?
Hello?
Hi.
Mr. G.
Loud.
When a super massive red star thing collapses, how fast does it take?
Ooh, that's a good question. It still takes a while. It doesn't happen instantly, but I don't know. Look it up for me. Okay, so all you need to know is that a baby star is called a protostar. That's a vocab word as well. That's when it first starts its nuclear fusion. It's a protostar. All right, Dylan, who's just looking at the ceiling? All right. Wait, what's this?
No, I'm not.
A protostar is a baby star. They said it in the video too. It's the first stages after gravity pulls all that gas in and it starts its nuclear fusion. Right when it starts doing its nuclear fusion gig, it's called a protostar, and that's the baby star. It's in the vocab too, so you might want to check out the vocab. Now, this is sort of interesting to me. The length of a star's life. Stars can last billions, sometimes they think maybe even a trillion years, depending on its size. And you would think, oh, the bigger the star, the more hydrogen it has to burn, so it'll last longer. But it's the exact opposite. Think of it like it says in this example, like a car. The big trucks, the big cars, like the Hummers and everything, they have bigger engines. I'll go slower. Bigger stars, bigger trucks, bigger things that, burn fuel usually use up more, like planes or anything. So the bigger stars use up their hydrogen faster, and thus their lifetime is much less than even our star. Our star is like a small star, so it lasts longer. There's even smaller stars than us that last even longer. So the smaller the star, the longer it actually lasts. So you need to know that. If I ask you a question of which would live longer, a big star or a small star, you'd have to know a small star. Small stars don't burn their fuel as fast, that's all. So our star, a medium-sized star, how much longer, because I think I want to rewatch the vid. I don't know, I feel like it's going to be a little while. Sorry, Lana. It's okay, you can go watch later. Generally, so our star is probably living for 10 billion years. Like a super giant, so this is our star right here, this yellow one, like a super giant, like a blue one that's super hot and everything, might only last 10 million, which is like 1% of the lifetime of our star. So they're very short in comparison. Yeah, this says like a small one can last up like 200 billion years, which is pretty crazy. You do have to know that a normal healthy star in the middle of its life is called a main sequence star. If you want to write that down, Elena. Main sequence star. So all you need to know from this one is that usually the length of a star's life is related to how much mass it has. The more massive, the shorter life it has. It burns up fuel faster. because I missed the formation of the stars. Oh, this was just that. You should already know it from last week, Elena. That there's the nebula, gas, and hydrogen. They start collecting, and then gravity starts pulling them all together, and then eventually there's so much pressure that they start to fuse with each other. And once the hydrogen atoms start fusioning, that's nuclear fusion, and then it starts emitting radiation and becomes a protostar. I went too fast again, sorry. You just have to know that gravity forms the stars by pulling all the gas in from the nebula and then makes a protostar. That's it. I'm sorry, Dylan. I'm sorry. I will go slower for you. Yes, Elena. All right. Did everyone get this one done? This one just says that the life of a star depends on how big it is. The bigger the star, the shorter the life. The smaller the star, the longer the life, because bigger stars burn more fuel. Oh, Edward, you wanted to know how fast a supernova explodes out? I thought you wanted to know how fast it happens. From when it runs out of fuel to when it actually explodes. Okay. Can I move on to the next line, Elena? Gerald says yes. So I'm gonna do it. Too late, Elena. All right. So we're not really going to talk about the stars when they're healthy. So we went from protostar, and then the star's healthy, and now we're at the end of its life again. All right. So at the end of its life, when it runs out of fuel, which I've already sort of talked about, the outer part of the star sort of expands out, and then it becomes, in our sun's case, a red giant. So smaller stars to medium stars become red giants when they hit the end of their life. So medium to small stars become red giants. Giant stars, which we'll talk about in a second, become super red giants, like Super Saiyan. So when our star runs out of fuel, the outer portion will expand. All right. Now the outer portion, when it expands, will, if there's planets around, it'll destroy the planets, like ours. But when it expands enough and then contracts and expands, it's going to get rid of a lot of it. It's like shedding its skin almost. And then once it sheds its skin, that gas is back out into the solar system. I'm going to go back in a second. It looks like these. This is what happens when the suns, at the end of their lives, shed their skin. They create planetary nebula. And it's very pretty. So that's what happens. So at the end of a sun's life, it becomes a red giant, and then those red giants sort of shed their skin and make those pretty little things in the sky as their last dying goodbye. But yes, Elena. Once they do leave, they create that planetary nebula. They leave something behind, and that's the white dwarf. The core of the star basically stays behind. What was the first thing I said on this slide? I said that when a small to medium star runs out of fuel, it becomes a red giant. It sort of expands. And then when it completely runs out of fuel, it sort of sheds its skin, and then just the white dwarf is left behind, the core. All right, the core is usually the size of Earth. It's very small compared to the size of the original sun.
What happens after the core goes away?
No, the core is, it's sort of still there. It's the white dwarf, and it stays a white dwarf, just sort of glowing, There's no nuclear fusion going on anymore, but it sort of still glows from the energy it used to have for a long time. Like billions of years, actually.
What happens once it runs out of energy?
It just becomes black and dark, and it's just another rock in space made of carbon.
So all those space rocks are probably dead stars.
Never know. Could be. Could be little dead stars. Yes. A red giant is just the star, a regular star, not a big star, a regular star at the end of its life. It sort of gets bigger, and it's called a red giant. And it's called a red giant because it gets bigger, and then it turns red. And we'll learn about the fact that red actually means colder as far as suns go. So it gets cooler and gets bigger. Sort of like I will. Towards the end of my life, you know, I'll get fatter. Yeah, that sort of thing. Okay. So, you know, white dwarf is the last part of the sun's life, a normal sun's life, not a big sun. All right. Sort of sad. Then the sun just goes away.
What happens if a white dwarf goes into a black hole?
It's just gone. Black holes just eat suns. Like, that's happened actually recently. They can just take a sun and go bye-bye. All right, and this is what we already know. This is when the normal star sheds its skin. That's what happens, a planetary nebula. They're very pretty. Is the core a white dwarf? I mean, it's not necessarily the core of the sun, so to speak, but it sort of is. It's like what's left at the middle of the sun after it sort of dies off. Yeah, once it sheds its outer layers, just like it's made out of so in the beginning, a star is burning hydrogen. And then to burn hydrogen, it smashes them together. And when you smash hydrogen atoms together, it makes helium. And then once it runs out of hydrogen, it smashes those helium atoms together, smash, smash, smash. And when you smash helium atoms together, it made carbon. And carbon is solid. You can't really use it for fuel. So what's left, a white dwarf, is mainly a solid mass of carbon that has no more helium or hydrogen to burn off, so it can't do the nuclear fusion anymore. So it's
Then
just
how come
the sun.
has light?
Yeah. What?
How come it has light then?
I don't know exactly what they said, but what I saw is just the leftover energy. I don't know why it still emits light. Maybe it's like radioactive or something. But all right, so now the other way, if the sun is super big, it does not turn into a white dwarf. It does not. It turns into a supergiant, not a regular red giant, and it's like ginormous, absolutely huge, okay? And then after a supergiant runs out of fuel, it goes boom, and you can't even describe how bright it is for us to be able, we see them not quite often, but we've seen them happen from Earth, which is sort of insane for how far away they are. And that's a supernova explosion. From a supernova explosion, enough energy can be made to actually eventually that dust that it creates from the explosion make new stars. Like you can have a recycled star made from a supernova, which is sort of cool. It's not going to be as big, but a new star can come from a nebula made from a supernova, which I think is sort of cool. They believe, and you don't need to know this for the test, you do need to know what a supernova is. It's just an explosion that comes from a supergiant. But they think that our solar system was made from a star that went through supernova, and then the star dust from that supernova became our sun and the planets. So technically, our entire solar system, and including us, is made from stardust. Ta-da! We're made of stars. You're a star, Elena. You're a star, Dylan. See? Our parents were wrong. We're not losers. Superstar.
What happens if a supernova explodes nearby the Earth?
I don't think it will. We have no red giants, super giants anywhere near us, so we don't have to worry about that. I would assume the only thing we would have to worry about from a distant supernova is just the radiation that it would send our way. But the sun usually protects us from most of the radiation of the solar system. So I think we're worried.
How does it protect us?
It's magnetic field. Our magnetic field protects us from most radiation, actually. Our magnetic field protects us from the sun's radiation, and the sun's magnetic field protects us from the gamma rays and other radiation from outside our solar system. Because there's a lot. Like outside our solar system, there's tons of cosmic radiation trying to get in. All right, I'm going, Elena. Let me look. Say the slide again on how we should write it. Mr. G, say the supernova slide again. I didn't hear you. Mr. G, say the supernova. Dylan, is that a sticky note? Okay, so the only way a supernova can happen is from a supergiant, which is a massive star at its end of its life. Once it runs out of fuel, it goes boom in a supernova, and that's all I want you to know. The other stuff is like a bonus, all right? That supernovas can make new stars and new nebulas because they're so massive and the energy created, and that we come from a supernova, they think. Just the first part, the first two sentences, those two. Massive stars make supergiants at the end of their life, and then when they run out of fuel, they go boom. They go boom.
So people think that we were created from a supernova.
They think our solar system was made from old supernova, yeah, near us. Yep. And they also, that's sort of the idea of the Big Bang Theory, is that there was just one giant supernova sort of type of thing. What's that noise? Get that nonsense out of here. All right. Sorry, Lena, we're moving on. We have to, because everyone else that's going to watch this is going to be like, why can't we move on? I'm watching this video. I guess they can just sort of skip through the video. I think I tried to show you guys what a supernova would sort of look like. I don't know if this is going to, yeah. That's sort of what they think a supernova would look like if you were close to it. Pretty big. All this stuff is new nebula. All that gas that's exploding stars can be made from again. So do I leave space on my page? I guess. I think there's a customer on the patio. Oh, you're at your restaurant. That's sort of cool. All right. Okay, so then after a supernova, those things can happen. All right? There's two different things that can happen. One, the material left from a star is behind. Yes, it can form a neutron star. All right? Neutron stars are super dense. They can be like, I'm trying to think. They can be like the size of Los Angeles, but be as heavy as 10 suns. They are super heavy and super small usually. Trying to describe what I want you to know though. You know what? Don't worry about that. Just know neutron stars come from supernovas, and they're very dense and very heavy and very small. That's it. I'm not going to make you remember what pulsars are or that neutron spin and stuff like that. You guys don't need to know that stuff. That's too much.
Will it be possible in the future, like something in Star Wars, where they drain an entire star and they blow up planets?
I don't see why not. I'm recording the video right now, Elena, so you can't watch it yet.
What's at the end of a black hole?
What?
What's at the end of a black hole?
Nothing. What?
I don't know.
The most, okay, so, and then you also have to know that after a supernova, if it's, you know, if the sun is absolutely huge enough, it will make a black hole after its supernovas. It just has so much gravity, it pulls everything inward and just makes what they call a singularity, but you don't need to know that. All you need to know is that black holes are made from giant stars when they explode. That's all. Black holes are made from giant stars when they blow up.
Nothing else.
And they have a ridiculous amount of gravity, which sucks everything in. That's all. As long as you know black holes come from ginormous stars that supernova, like the biggest of the big, and they have a ridiculous amount of gravity that sucks everything in. Just like this video.
Wait, so it's sucking in that star?
Yeah, black holes can eat stars all the time. There's actually, if you look it up, there was one, I think a couple of weeks ago, that they actually watched a black hole eat a star. Yeah, you can look it up.
Okay.
It's very, like, obviously, watching it so far away, it looks very blurry, but the fact that they can even see it, period, is sort of amazing. Okay. And we already know this. There's two ways the stars can live. If it's a big star, it goes down this route. If it's a regular or small star, it goes this way. All right? Any questions about that? Okie pokey. Do I want to make you guys watch this video? Yeah, why not? Okay, this is super cool in my opinion. I learned this, I don't know if I might have learned this in high school. You guys are learning in middle school. You might think, like, you know, people say all these things, wait, say that again, about black holes. The drawing. Oh, there's only two ways. Regular average star or a small star takes this road, and then massive stars, what it says, go this way. That's the only two ways. That's what happens. That's it. I don't know how it's going to be on there. You do have to know that average stars become red giants and eventually become white dwarfs. And then massive stars become supergiants and they do a supernova and can make a black hole. So you sort of do need to know it. I don't know if I'll put this drawing on the test or not, though. I might. Everything is hard. This is hard stuff. So it's really, they found a way to look at something in space and they can figure out exactly what it's made out of, which is the coolest thing ever. Like, they can look at a planet or they can look at a star and they can say, oh, that thing's made of hydrogen, or oh, that's made of helium, and they're not even there, which is really cool. And they do it by looking at its colors, which is sort of weird. And this is sort of, I don't know, if this is too much over your guys' head, then don't worry about it, but I think it's super cool. Let's see.
If you look up at the patches of or perhaps Orion's belt. But hold on, look at that murky patch again, and hold out your thumb. How many stars do you think are behind it? 10, 20? Guess again. If you looked at that thumbnail-sized patch of sky with the Hubble Space Telescope, instead of points of light, you'd see smudges. These aren't stars. They're galaxies, just like our Milky Way. Cities of billions of stars, and more than 1,000 of them are hidden behind your thumb. The universe is bigger than you can see from a city, and even bigger than the starry sky you can see from the countryside. This is the universe as astrophysicists see it, with more stars than grains of sand on Earth. By staring up at the stars at night, you've taken part in the oldest science in the universe. Study that emphasis on navigation, agriculture, perhaps even language itself. Yet, unlike other sciences, astronomy is purely observational.
We cannot control the parameters of our experiment from lab benches. Our best technology can send man to the moon and probes to the edge of the solar system, but these distances are vanishingly small compared to the yawning gulfs between stars. So how can we know so much about other galaxies, what they're made of, how many there are, or that they're even there at all? Well, we can start with the first thing we see when we look up at them, the stars. What we are trying to learn, the properties. What are they made of? How hot are they? How massive? How old? How far are they from Earth? And believe it or not, we can learn all of these things simply from the light shining in the sky. We can decipher one kind of stellar message by turning starlight into rainbows. When you look at a rainbow on Earth, you're really looking at light from our sun being scattered through water droplets in the atmosphere into all the different wavelengths that make it up. And when we study the light from other stars, we can create rainbows on demand using not water droplets, but other specific instruments that disperse light. When we look at the scattered light from our sun, we see something strange, dark lines in our rainbow. These lines are the characteristic fingerprints of atoms. Each type of atom in the solar atmosphere soaks up light at specific wavelengths, and the amount of absorption depends on how many of these atoms there are. So by observing how much light is missing at these characteristic wavelengths, we can tell not only what elements are in the sun's atmosphere, but even their concentrations. And the same idea can be applied to study other stars. Make a spectral rainbow, see what's missing, and figure out which elements are present. Bingo! Now you know what stars are made of. But we aren't restricted to just the wavelengths that our eyes perceive. Consider radio waves. Yes, they can bring the Billboard Top 100 to your car, but they can also travel almost unimpeded in space. It can tell us the very early history of the universe, from just a few thousand years after the Big Bang. We can also study the infrared light emitted by colder objects like the gas and dust clouds in space, and the ultraviolet light from the hot stars recently born from those clouds. Studying different wavelengths not only gives us a more complete picture of any single object, but also different views of the universe. For this reason, astrophysicists use several different kinds of telescopes covering the spectrum from the infrared, the ultraviolet, to the X-ray, from giant radio dishes to giant silver mirrors to space satellites, detecting light that would be otherwise blocked by the Earth's atmosphere. Astrophysicists don't just see the billions of stars among the billions of galaxies in the universe. They hear, feel, and sense them through many channels, each revealing a different story. But it all begins with light, the kind we can see and the kind we can't. Want to know the secrets of the universe? Just follow the light.
So they can actually use the wavelengths and colors to figure out what things are made out of, which is really cool. I learned that. I've actually used something, and I've actually looked at a star, our star, and figure out what it's made out of, which is really cool. Wait, how did I do this again? I did it again, didn't I? Okay. All right, I'm gonna try to go quickly because I didn't realize how much time we've been doing. Mr. G, are you being attacked by aliens? Yes. Okay, so this is the last thing, and this stuff we're about to go over right now is pretty much what your project this week is on. This week you have to, is a project just like the pollution thing. Pick any star you want. You can pick our sun if you want, or any star. Just look up anyone you want. You can pick a small one, a big one, wherever, and you have to tell me all about it. And this is the stuff that you have to tell me. Sure, Kevin. All right. The star, there's different properties of a star. And then there's actually, Elena, one here missing, and it's age. The color and temperature, its size, its composition. Remember, composition is what something's made out of. Its brightness, and its age. That's how, when we sort of compare stars, those are the things we talked about. You paying attention this time, Andres? I'll wait. Because Andres did not do so good on his last quiz.
Okay.
Yep, you just got called out. All right, June. All right, so first is color and temperature. We're gonna talk about all of them. Color and temperature, and then you guys might know this about flames already, but the blue flames are actually the hottest. So the blue stars are the hottest stars. Then the yellow stars, like ours, are in the middle. And then the red stars are the lowest. Remember those red supergiants and giants? At the end of their life, the stars actually get colder. And that's why they become bigger and then they become red, because they start running out of fuel. If you're looking at these, K is actually Kelvin. Kelvin is a form of temperature like Fahrenheit. 0 Kelvin means it's absolute zero, like there's nothing moving. We talked about that. It's like negative 273. A stove is like a hot stove where you burn yourself is 473 about Kelvin. So if you look at these numbers, it's really high, really, really high. And those are just surface temperatures. Those aren't the temperatures at the core of the stars. Yes, our sun is like a yellow, orange, or a yellow star. We're towards the bottom, or the middle. I might, I probably will, one second, Elena, we'll give you different charts and stuff on the test, and you'll have to figure out what type of star it is. I'll either give you, I'll say something like, which is hotter, a blue or a red star, or I'll give you this, and you have to figure out which one's a blue star and which one's a red star based on the temperatures or something like that. You just need to know that Kelvin's a form of temperature. That's all. You don't need to know like how hot something is in Kelvin. You do need to know Kelvin's a temperature. Just so you don't like look at this and like, wow, blue stars have $60,000. That's great. How much did you write already? All right, well, that's good. So yeah, you just need to know blue's hot, yellow's in the middle, red is the lowest temperature of a star. Red stars are low. Oh God, Elena, you write too much. What is that, a super row? What are you talking about, 0? Oh my goodness, Elena. And you write small too, so. All right, so after color and temperature, they often look at the size. And when a scientist talks about the size of something, or you see a chart that talks about the different sizes of the suns, like that, Elena? All right, so I'll try to go slower. I'm sorry. We're just, this video is already over an hour long. When we talk about the size of a star, it's very simple. So if I say that star is a size sort of 2, that just means it's twice the size of our star, our sun. That's how they do it. So if it's a 4, it's 4 times the size of our star. If it's a 200, it's 200 the size of our star. If it's a 0.5, that just means it's half the size of our star. All right? So the number of the size is just compared to our sun. They do that with a lot of things. Is that a little better, Elena? Am I doing better? Jaden? Okay. And obviously, we've already talked about this, but the bigger the star, usually the shorter its life is, because it burns up fuel more. Smaller the star, the longer it lasts. So that's why we shouldn't feel so bad that our star is not too big, because it'll last a little longer. All right, next. This is the video, that confusing thing, all right? Now, you do not have to write down everything, Elena, but you do have to write down that we characterize suns by their composition, and you just have to remember that composition is what the sun is made out of. Usually, on average, most stars, it says, are about 3/4 hydrogen and helium. So hydrogen and helium, once again, are the main ingredients. You have to know hydrogen and helium are the main ingredients of all suns and stars. I don't think I'm gonna make you do this. If we were in class, I'd probably make us all do this, but like, you can literally look at the little special telescopes they have, and you'll see stuff like this, and you'll see missing lines of color. And you would have to be able to look at the missing lines and say, this is what, say, Elena, A right here is our sun. All right, I was looking at our sun in the special spectroscope, and I'm trying to figure out what it's made out of. So I'm looking at these missing lines, and I'd be like, all right, so this hydrogen has 2 missing lines in the purple. So I see, all right, there's 2 missing lines in purple here. It has 1 in the blue. There's 1 in the blue and 1 in the red. So it probably has some hydrogen in it. And then I'll go to helium. This one also has 1 in the red. So you have 2 in the red. You just sort of line them up. 1 in the yellow, 1 in the green. So this is our sun. It's made out of hydrogen and helium. And that's how you sort of do it. You just line it up. I'm not going to make you guys do this. More and more I would go through this entire chapter, I realize how much I'm throwing at you guys. You just have to know that the sun's made out of hydrogen and helium, mainly. Like 90% at least. I'm waiting. Wait, what? Oh, I just said at the beginning, they characterize stars by what they're made out of, their composition. Most of it's made out of hydrogen and helium. As the star gets older and older, it'll become less hydrogen and more helium because it burns up all the hydrogen. And then as it's dying, it'll turn from hydrogen to carbon. But you don't need to know that. That's just me being geek. Nice sombrero, by the way. How do I say Jafio to describe Mr. G because he talks so fast? Jaffio? What? I talk so fast because it's going so long. Yeah. In class, I would have done something with this, but you just need to know that they look at suns to see what they're made out of. Most suns are made out of helium and hydrogen. I'm waiting. Going like this doesn't change anything. So whenever you do your project and you're looking up different things of the sun, I believe one slide of the project is to say, what is your sun made out of percentage-wise? And that's what composition is. So you'll have to say, oh, this sun is a blue giant or whatever, and its composition is made out of 99.9% hydrogen. I don't know, something like that. You just have, and you'll be able to find that information just by Googling it. It won't be too hard. Then put a pretty picture on the slide. Hello, Elena. How much longer? We're almost done. I'm sorry, you don't have to stay here though. So I just write helium. Yeah, that's fine, Elena. You don't have to worry. This is important though. This one's important, so pay attention. A big factor that they talk about stars with is called brightness. They also call it luminosity. Luminosity is the same thing as sort of brightness. If a luminosity, they sort of compare it to the sun again. If a star is a 5, if it's a luminosity of 5, that means 5 times as bright as our sun, just like the size. A star with a luminosity of 1,000 is 1,000 times brighter than our sun. Same thing. And these vocab words are very important, Elena. The 2 at the bottom there. Apparent brightness and absolute brightness. Elena, or let's go, since Elena's writing. Jaden, do you remember what the word apparent means? Apparent means what it seems to be, what we think it is with our own eyes, what it appears to be. So it's not actually how bright the star is, it's what we see, how bright it seems to us on Earth. So apparent brightness is how bright the star appears from Earth, from us looking at it. It could actually be extremely bright, which is very far away, so it doesn't seem as bright. So apparent brightness is just how bright it seems. And then absolute brightness is actually how bright the sun is. If you were trying to figure that out, you'd line up all the suns so they're right next to each other, and you can compare how bright it is. That makes sense, Calvin? Ish. Apparent is what it seems, and it can change on how far away it is. Like a star could be like sort of dim, but it's just so close. And then Elena just gave up and started playing the ukulele. She gave up. She doesn't care anymore. Elena never cared. I see how it is, Elena. Oh, you're finished. Okay. I will probably give you something like this on the test too, that chart. And this chart is very cool. It's sort of, you know, all the stars are categorized here. The bottom is temperature, and this is how bright it is. Remember, all red. Red is the lowest temperature, so all red will be here, and the further you go over here, blue. White dwarfs, since they are not burning up any fuel anymore, are not very bright. The brightest ones are the biggest ones, obviously, for the most part. This is just one of the diagrams that they use to classify everything. Let's see, I mean, a question that I could put on your quiz or test could be, I could get rid of, you know, these names and ask what is this set or something like that. Or which is brighter, blue giants or white dwarfs, and you'll have to know, okay, they're up here, stuff like that. How hot are white dwarfs? Well, it says right here, they're very hot still. As they're cooling down, I'm sure they cool down, but they're still very hot. Once it turns to a black dwarf, what's brighter, a dwarf or blue? Blue is obviously up. Further up you go, the brighter it is. And obviously you can see the bigger it is too. So the size has to do with how bright it is. So what is white hotter than red? Yes, white is hotter than red. It goes red, orange, yellow, white, light blue, blue. I think that's it. Oh, I might give you something like this too. It's sort of the same thing. Let's see. Circle the words. So if I have a red-orange one, that's 50 Kelvin, high brightness. So red-orange, 50K. So it go right here. That's red-orange. And then high brightness. So I'd go all the way up. So it could be some of these guys in here. So you'd have to do that and just find out which one's which, something like that. Oh, I don't know. We're not watching this video. We've already seen it. That it? All right, we're done. Yeah, we get 10K. Yep. Let me stop the recording at least. I want to stop the recording.